Hi guys, Dr. Diaz here again, and now we're going to discuss about magnetic field and magnetic forces. And as you remember, there's only four fundamental forces in nature. Here is gravitational force, electromagnetic force, nuclear interaction weak, and nuclear interaction strong. These are the four fundamental forces in nature, and we already discussed gravitational force, right? That was last semester. We discussed electric field. Now we're going to discuss magnetic field. And if you remember about these forces, this one is the strongest one, then this, then a combination of these two, and finally the gravitational one is the weakest one. So let's go to magnetic field. Look what's happening here. Here they give us a little bit of definition of magnetic field. But I'm going to draw something here. Okay, I guess everybody know what is this. I'm drawing here. Looks like a rectangle kind of thing. Let's assume that this is a magnet, and the magnet, you all know that it has an N and an S. If you cut a magnet in half in order to try to isolate an N or an S, what you would have is two small segments with an N and an S. So you will have two small magnets. And if you cut this one in half, you will still have two small magnets, with an N and an S. And if you try in order to isolate an S or an N, you can't do that. That means that there is no such thing as a magnetic monopole. And actually, one of the equations of Maxwell, it tells you that. But we're not going to discuss the equation of Maxwell. That's actually a little bit of advanced physics here. But at least I'm telling you, there's no such thing as a magnetic monopole. Crazy people even wrote in the book Jackson, which is a classical electrodynamic group for doctoral students. I took that one. I actually have one in my office. And there's a section in the paper that someone talks about it, that they discovered something, I think in the 40s, but they haven't been able to replicate the experiment. Well, that thing doesn't exist. But Alan Gould says that in the early stage universe, in the inflationary universe, there might be magnetic monopoles, but so far we haven't seen those things. So there's no way, if you cut a magnet, you will be able to isolate the S or N. There's no way. So let's go in here, keep going with the definition. A vector coming out of the page represents a dot, which can think about like the point of an arrow of a magnetic field. Well, here's what they're saying. Let's draw here Cartesian coordinates. Well, it's actually, this is in 3 dimensions. We have put here Y, let's put here X, and let's put Z. Okay, what had happened is, if you have points or dots like this, it means that the magnetic field B, which is the letters we're going to use for magnetic field, which in reality, this is actually magnetic density, but it's okay. But let's use it as magnetic field. Oh, they have it, they call it here B out. It goes out toward you, out of the screen. If you have arrows like they have it here, that magnetic field goes toward the screen. Now there's something called the right hand rule, that if you use your hand, you can tell more or less the direction of the magnetic field if you know the direction which the particle is moving. Suppose that you have a particle that's moving in this direction. It has a velocity v, and the magnetic field is going outside the screen toward you. If you use the right hand rule with your index, the middle finger and your thumb, your index is always going to point in the direction of the velocity, and your middle finger is going to point in the direction of the magnetic field. And if you do that, you will see, try you guys at home, that the magnetic field, the direction of the force is actually down. And we will see this later, because the equation is force is equal to Q, let's put, well, absolute value Q, B cross B, right? And because it's a cross product, it means, well, it doesn't obey the commutative property, which means B cross B is not the same as magnetic field times vector velocity. We will see this in a second, but it is important to know this equation. It's important to know the direction. And if you have seen the book, or read a little bit of the book and search a little bit, I mean the information I give you to look at it, you will see that they tell you in details how the magnetic field is being calculated by using the right hand rule. Okay, so let's go to see this inspection can be used in any type of vector we will encounter magnetic field, velocity, and force. So here we go. An electron moving in a magnetic field. Oh, looks like the screen of a TV there, not there, right? So you remember the equation I was telling you a moment ago for magnetic field is something like this. Well, let's put it up here. F magnetic force is equal to what? The charge of electron B cross B. And if you want to find the magnitude of that force, the magnitude, then in that case V is going to be equal to Q B sine of the angle that is formed between the vector velocity and the magnetic field. Look at this example. It says an electron in the old-style television picture to move toward the front of the tube with a speed of, look at that, the speed of the electron, 8 times 10 to the 6 meters per second. It's going pretty fast. The surrounding negative tube are closed wire that create a magnetic field, and the magnetic field here is, I forget to tell you something. What is the unit for magnetic field? I should put it here. We know that force is measured in newtons, right? Charge is measured in coulombs. The velocity is measured in meters per second, and the magnetic field is measured in something called Tesla. Yeah, it's not that guy Elon Musk or whatever. It's in honor of Nikola Tesla, who is, well, we said today, it's been said that he's the inventor of the modern radio, and he did a lot of experiments in real life. And actually, he worked with Thomas Edison, and he was one of the proponents, along with George Westinghouse, of the AC generators, which is actually electricity thing that we use today. Yeah, well, you can see, you can read about Tesla, all his fight with Edison, even that he one time was an assistant, and you know, when Westinghouse and all the inventions and generators and electricity, he did a bunch of stuff. There's actually a movie with Gene Hackman and I'm not sure what's the other name, the guy, Christian Bale, something like that. I think it's the Prestige, in which Tesla is actually is David Bowie actually is the actor doing Tesla. Interesting movie. And it talks about some stuff that supposedly Tesla did. I'm not sure it's right, but here we go. But the thing is, we're going to use this equation to calculate the electric field, right? We're going to use this equation to calculate the electric field. I mean the magnetic field. And how we calculate the magnetic field? Well, let's go. In this case, it's the magnetic force. Here we go. To calculate the magnetic force on the electron, we use the equation. We got it. We put here the charge of an electron, which is 1.6 times 10 to the minus 19 coulombs. We multiply by the speed of the electron moving through the field. We calculate it. We multiply by the magnetic field that is present in while the electron is moving through it, and the angle that is forming between these two. If we go back to the problem, it is with an angle of 60 degrees. Here it goes 60 degrees. The direction of the electron through the magnetic field, and the magnetic force, according to the right hand rule, is going to be upside down. It's going to be down. And then we get that the magnetic force is 2.8 times 10 to the minus 14 newtons. You know, magnetic field, if you look here in nature, what's the magnetic field of the Earth? The magnetic field of the Earth is actually pretty small. It's like 5 times 10 to the negative 5 Tesla. You actually can create magnetic fields much more intense than the magnetic field of the Earth. Well, yeah, that's it. Okay, guys, I will do another example and talk about a magnetic field and how it moves around, how it moves in circle and all the equations related to it. See you in a second. Bye.